Okay, now we're going to talk about risk. And the things we're going to do is, first we're going to start with expected value, then decision trees. The decision trees look a lot like the decision trees we were working with in game theory. We're talking about techniques to reduce uncertainty and find the expected utility. Right? In other words, instead of just the expected value, we said how much utility we're going to get in those. And the payoff or the circumstance that gives you the highest expected value does not necessarily give you the highest expected utility. We're going to define risk as hazard or the chance of loss. And probability, we talked about that the first day, the likelihood and chance that something will happen. Right? Our frequency definition of probability, events that limit the frequency of a large number of trials. So the probability of an event, we'll call it A. We're going to denote it P of A. And it's simply the number of times that an event will occur, in this case, event A, over the total number of trials. And hopefully that'll be a large number to give us what we call the law of large numbers. In other words, put us close to the actual probability. I can define something known as subjective probability, right? The degree of a manager's confidence or belief that an event will occur. Some of the rules of probability is that the probability has to be between 0 and 1. It can't be less than 0 and it can't be more than 1. Right? And given a list of mutually exclusive events, collectively exhaustive lists of events that occur in a given situation, the sum of all the probabilities has to equal 1. Right? So the sum of all possible events, right? The probability of each of those events, sum them up, it has to equal 1. So the next thing I'm going to do is we've talked about our weighted average. I'm going to tell you what expected profit is. Oh, I'm sorry, probability distribution. It's a table that lists all possible outcomes and the probability in terms of each outcome. I don't know why they separate out. They should have put this in a different slide, but expected profit is simply the profit times the profit given an event, or in this case, a state of nature, right? Times the probability that that event will occur. I sum them all up, and it'll give me my expected profit. Does that make sense to everybody? If not, I'll give you an example soon, and hopefully it'll become clearer. Where pi I is the profit associated with outcome I, and pi is the probability of outcome I. So here's our example, right? There's a 50% probability that I'll make $800,000 in profit, but there's a 50% probability that I'll lose $600,000. Right? So basically, I multiply profit by the probability and sum them up. So 800,000 times 0.5, that gives me 400,000. Negative 600,000 times 0.5, that gives me negative 300,000. I sum the two, 40,000 plus negative 80,000 gives me 100,000. Right? That's my expected profit from this pricing and advertising decision by Jones Corporation. Right? Also, that the payout from not increasing the price, right, and not doing advertising gives me 200,000. So my best strategy in this case is to not incur the new strategy of pricing and advertising. In other words, don't do it and just take the 200,000 instead of, right, an expected profit of 100,000. Even though it's possible that if I do this, I make 800,000. Right? But the expected profit is only 100,000 because it's also possible that I'll lose 600,000. So that brings us to our decision tree, right? So if I increase price with the new strategy, right, my expected profit is 100,000. If the campaign is successful, though, I make 800,000. But if it's not successful, I lose 600,000. If I don't increase price, I get 200,000. Okay, so we saw that the best strategy is not to increase price and just take the 200,000. That brings me to the following. What if I can pay somebody to give me a crystal ball that'll tell me whether the event is successful or not, or would be successful or not? How much would that crystal ball be worth to me? Right? And that brings us to the expected value of perfect information. If I knew, right, if the campaign would be successful or not, or if I could pay to find out if the campaign is successful or not, how much would it be worth to me? So my increased profit from completely accurate information, right? In this case, given perfect information, the company will increase if the campaign is successful and make 800,000. But I won't increase the price if it wouldn't be successful. So in that case, I'd make 200,000. So in this case, my expected profit, if I had perfect information, would rise from 100,000 to 500,000. 800,000 plus 200,000 divided by 2. So what that means is the expected value of the perfect information would be that expected value, 500,000, minus the 200,000 for me not increasing price. So the expected value of perfect information in this case would be 300,000. That's how much that crystal ball would be worth. Okay. Here's another game tree example. In this case, I have Genco, who's an oil exploration company, right? And they're deciding whether to drill in a specific location or not. If they don't drill, they don't make any money, $0. But if they do drill, right, and they don't find oil, they lose 90,000. If they find oil and that well produces 10,000 barrels, they make 100,000. If that well produces 20,000 barrels, they make 300,000. And finally, if it produces 30,000 barrels, they make 500,000. Now, the probability that they don't find oil is 60%. The probability that that oil well produces 10,000 is 13%. The probability that it produces 20,000 barrels, again, would be 15%. And finally, the probability that it produces 30,000 barrels, 10%. So, that, give me a second, you'll see. So, to get the expected profit from drilling, right, I multiply all my probabilities, right? So I get 26. No fraction. 26 times -1,000 plus 0.15, or 15% times 100,000 plus 0.5, which is 20,000 barrels, and made 300,000, and then plus 0.1. If 500,000 the well produces 30,000 barrels, and that gives me an expected profit from drilling of $56,000. Okay. So I have a choice. In this case, my expected profit is 56,000 from drilling the well. That's my expected profit. And not drilling is 0. So we're gonna do this later on. If I'm risk neutral, For risk seeking, I'm definitely going to drill the well. If I'm risk averse, then I may or may not drill the well depending on how risk averse I am. Right? Because there's a possibility that I'll lose 90,000. Okay. Another example, suppose I have a small business and they can make a certain profit of $2 million. But they can enter a gamble, and this can be a profit or it can be just a roll of the roulette wheel, where they have a 50-50 chance of making $4,100,000, right? Or losing 60,000, right? So if I take that 0.5 times 4.1 million times 0.5 times negative 60,000, I get an expected profit or expected value from the gamble of $2,020,000. Now, my question to you is, what would you do? Nobody wants to look at me. Everybody's looking away. What would you do? Would you take the 2 million or would you take the gamble that has an expected value of 2 million? You'll take the 2 million. You are a risk averse. Would anybody take the gamble where you can make the $4 million, but you have a possibility of losing $60,000? Okay, you're resisting or risk loving. Anybody else? Okay, risk averse. Okay. So basically here, if the business is risk averse, right, they're going to take the certain profit. If they're risk loving or even risk neutral, right, they would take the gamble. So we talked about utility function. In fact, that's some of the first things we talked about. But we measured, before we were measuring the utility function in terms of goods consumed. Here we're going to measure the utility function a little differently. Here we're going to measure the utility function, right, as a measure of wealth. Right? The more wealth I get, the higher my utility is, right? Because I can consume more goods. So my utility function is a function used to identify the optimal strategy for managers conditional on or risk. That definition is a little complex for what we're actually doing. But basically, our utility depends on wealth, right? And here I have two outcomes of wealth, and I can compare the two within my utility function. Right? So we're going to construct the utility function. Expected utility is the sum of the utility of each outcome times the probability of the outcome's occurrence. Okay? So I'll get a certain payoff if one state of nature occurs, and that payoff is going to give me utility. So I take all of the, expected values in the outcome, measure the utility in those cases, right? Sum them up and do a weighted average according to the probabilities of each of those, and that'll give me my expected utility. Hopefully that'll become clear. Here we're going to construct the utility function. So I'm going to arbitrarily assign two levels of payoffs, right? One with the certain profit of the $2 million. And in this case, I'm sorry. In this case, what I'm going to do is I'm going to take Genco. I'm going to take these payoffs, right? And I'm just going to use the highest, which is 500K, and the lowest, which is 90K. Right? And I gave probabilities over here, but here I'm not going to do it yet. I'm just going to call it P and 1 minus P. So I'm going to say that utility for losing 90,000, if I drill, gives me zero utility. I could have said negative, but zero is a good starting point. And I'm going to assume that if it produces 30,000 barrels, right, and I make 500,000, my utility is 50. Right? So measuring those two, I ask, the decision maker what value, what probability would make any difference, right? Between a certain amount, say 100, right, and the following gamble. P times my utility of 50 plus 1 minus 3 is my utility of 0, right? Suppose I set P at 0.4, and the probability that I get the highest payoff, of course, according to our example, is only 0.1. Right? In this case, suppose the probability is 0.4, so I get 0.4 times 50 plus 0.6 times 0 gives me an expected utility of 20. Right? I continue this method. It'll allow derivation of any possible payoffs. In other words, I can do instead of 9,500, I can do something 0, 100, 300. I keep doing that, and I get a utility function where on the horizontal axis I have well, right, the well and current, and on the vertical axis I get my utility. So here, if I don't strike oil, right, I lose 9,000 and my utility 0. Right? If I get $0, I don't do it, my utility is 10. If I drill and I get 100,000, in other words, 10,000 barrels, make 100,000, my utility is 20. If I get 300,000, then my utility is 40. And then I can derive my expected utility assigning probabilities to all these cases. And that gives me my utility function. Questions? Okay. Now we'll get into the definition of what we talked about earlier. Most of you would have taken that $2 million instead of the bit with, I said most, not all of you, instead of the gamble, which you can make $40,000, but you have the risk of losing $60,000. Those people would be known as risk averse. So risk averters, right, have a diminishing marginal utility of wealth. Risk lovers, on the other hand, right, these are when the manager prefers a gamble with a less certain outcome to the one of the most certain outcome when confronted with gambles offering equal expected wealth. Risk neutral is when the manager maximizes expected wealth regardless of risk. So a risk neutral person would have taken the gamble simply because the expected return was greater than the certain return. So he is either risk loving or he's risk neutral. The rest of us who didn't want to take the gamble are risk averse. Right? And in that case, their utility function is linear and their marginal utility is constant. They don't have increasing marginal utility or they don't have decreasing marginal utility. If you're a risk lover, you have increasing marginal utility. If you're risk averse, you have decreasing marginal utility with regards to wealth. So here I have a graph. Again, I have utility on the vertical axis, wealth on the horizontal. Right? Now, I can stay with W star for certain, or I can take a bet. Right? And if I stay with W star for certain, my utility would be UW star. I can take a bet where I either win H or lose H, right? In that case, if I win H, right, I have W plus H, and my utility will be up here above W star. However, if I lose H, my utility will be down here, and I'll have U2H. Sorry. Yeah. Okay. So, what that gives me is between here and here, right? My expected utility would be below my actual utility. So if I take W star, my utility is up here, but if I take this gamble, right, my utility is here, UH W star. That would be my expected utility from the gamble. If I have a bigger gamble where I either win 2H or lose 2H instead of just H, right? Up here, if I win, I'd be up here. If I lose, I'd be down here. But on average, right? Here, my utility would be U to a W star. In other words, it would be below taking just W star with certainty. Now, for the first bet, H, right? What if I was forcing this person to take that bet? There would be an amount that he could pay me or that he'd be willing to pay me to avoid taking the bet because he's risk averse. And that amount would be W bar. So in this case, I can take W star with certainty, right? Or I could, and I would choose that. But if you're making me take the gamble, I would be willing to pay that much, the difference between W bar and W star, right? That difference, and that surface speed angle between here and here to avoid the gamble, right? I would pay that much to avoid this gamble, or in other words, I'd buy insurance against the gamble, right? And that's the amount that I'd be willing to pay. Because at that point, it's giving me the same utility. It's taking the gamble, but it's the insurance. Okay. This is somebody with who is risk loving and has increasing marginal utility of wealth. In this case, W star, right? If you take W star with certain, it's here. However, if you take the big guy, you have to be here and here. The average of those two would give him utility above taking that with certainty. Therefore, we prefer the gamble. And he'd be willing to pay to take this gamble, right? How much would he be willing to pay? Well, that puts him on the credit. So he's he'd be willing to pay that much to take the gamble, whereas the risk averter would pay that difference to avoid the gamble, right? So this is a risk lover or a risk seeker. And finally, we have somebody who's risk neutral. He's indifferent. He doesn't care. You're going to make him take the bet? Okay, I'll take the bet. You're going to give him the money with certainty? Sure. He's indifferent. Okay. Questions? And these graphs are from your book. The same graphs. We have somebody who's risk averse. Right? They have the content utility function. Somebody who's risk loving. They have an increasing margin utility as well. And their utility functions convex. And finally, you have the linear utility function. Somebody who's risk neutral. Okay. If you guys remember the first day, I defined variance and standard deviation. This is just the standard deviation of profits, right? So standard deviation, the most frequently used metric for displaying the probability distribution to a signal. Standard deviation is simply the summation of the probabilities times that profit, that event, minus the expected profit, which is just average profit, the whole thing squared. Once I get the sum of all those squares, I take the square root, and I get my standard deviation. If I didn't take the square root, that would be the variance, right? Standard deviation is simply the square root of variance. Okay. What I didn't, actually I did, but what you might not have seen before that time is the following coefficient of variation. This is something that's used basically in finance. The coefficient of variation is simply the standard deviation divided by the expected profit, right? So if I have two distributions as follows, right? Which of these two distributions has a greater standard deviation? Come on, it should be easy. Top one? Everybody agree? Okay. Why does the top one have more or a greater standard deviation? Because there's more possibilities out in the table, right? Here, there's less variation or less variance. And variance is portion simply the square of standard deviation. Okay. Now get back to the certainty equivalence approach. Basically what I showed you in those graphs, where the person is willing to avoid the gamble or take the gamble and is willing to pay to do so, right? When a manager is indifferent between a certain payoff and the gamble, the certainty equivalent approach, rather than expected profit, can identify whether the manager is risk averse, risk seeking, or risk neutral. If the certainty equivalence is less than the expected value, then the decision maker is risk averse. God dang it. If the certainty equivalent is equal to the expected value, then the person is risk neutral. And finally, if the certainty equivalent is greater than the expected value, then the decision maker is risk loving. So adjusting the valuation model for risk, the present value of future profits, which the manager seeks to maximize, can be adjusted for risk by using our certain equivalent profits in place of expected profits. So here in the example, I'm going to give you a manager's indifference curve, right? With the expected value on the horizontal axis, the horizontal intercept of the indifference curve is the certainty equivalence of the risky payoff, represented by the curve. If the decision maker is risk neutral, the curve is just vertical. So in this case, if he was risk neutral, right? So in this case, right, if it's $100,000, then his coefficient of variation, standard deviation over profit, is going to just be zero. Of course, in this case, right, if his expected worth is 200,000, he's willing to take this as long as the coefficient of determination is 3.1 or less, right, at 200,000. So he's willing to take basically 3 times the standard deviation over the expected profit. Okay, so here's an example. Suppose I have a manager that has a bond worth 900 million, right? There's a 25% chance that the bond will default and only pay part of that 900 million face value. In this case, there's a 25% chance that they only pay 400 million, right? That means there's a 75% chance that they pay the full amount, 900 million. So the expected value, right, is 0.25 times 400 million, plus 0.75 times 900 million, or 775 million. That's the expected value. Now, suppose this manager has the following utility function. And of course, I can write that utility function, right, as just W, the square root of W, right, just the coefficient. In this case, I have it to 0.5. So the expected value is 775 million, but the expected utility in this case, right, is 0.25 times the square root of 400 million plus 0.75 times the square root of 900 million, right? So his expected utility is equal to 27.5. Okay. Now, given a utility function, I can convert that expected utility into wealth, right? So that means W is going to be utility squared, right? So in this case, 27.5 squared gives me 756.25. Right? Now the expected utility, the expected value of this bond was 775 million, right? But the value to this person, right, is 756 million in 2025. Right? So in other words, if I paid him that amount, he would sell me the bond instead of taking the risk of losing the 400. Okay? So the certainty equivalent should be the manager's reservation price for selling the bond. So if you offered him that, he'd sell you the bond. Suppose there's an insurance company that'll insure that bond. Call it LBI, right? This is what AIG used to do before they went bankrupt for the 2007 crisis. So the expected payoff, right, for LBI is 900 million minus 775 million or 125 million. That's the top value, which you have to pay 900 million minus the expected value. So the expected payoff is 125 million. The most the policy is worth to the buyer is the difference between 900 million and the certainty equivalent, which is 143.75 million, right? So the difference, that 143.75 minus 125, is his risk premium. That's basically, right, the difference between LBI's reservation price for the policy and the maximum amount the buyer is willing to pay. So LBI can charge, right, somewhere in between those two figures, and basically up to 143.75 million for the insurance of the bond. Questions? Am I going too fast? This is going a lot faster than I anticipated. Okay, so this is it. Here, my last graph, I have standard deviation measured by risk on the horizontal axis. I have the expected return on the bond, not the same, right? So if there's zero standard deviation, zero risk, right? It pays 8%. So you can take the bond with zero risk and 8%. And as the risk gets higher, well, your risk premium increases. Once you get past one standard deviation, when it gets two standard deviations, I expect a 12% return on that bond. So the risk premium a year would be 4. Right? The difference between 12 and 4. Okay. You sure I didn't get you fast? All righty. There was a girl that sent me an email, and I don't think she's here today, that she didn't make the test because, well, I'm not going to say why. She didn't make the test. I expected her today because when I tried to answer the email, it didn't let me. My Wi-Fi was down at the house, and then I forgot to answer her until today. And I figured it was just better to talk to her in class, but she didn't show up. So if you know her, have her send me another email. If you know the person, it's not. Oh, okay, look. That was the whole point, right? That was the whole point of me covering the two lectures today. You guys don't want the final lecture? No. Okay, Jorge. One. Camila, one. Andrés. Tengo dos Andrés. Javier González. Javier. I apologize in advance for Angelina. That's the technology. Oh. Speaking of which,